was struck by a frightful but short-lived stomach ache. Drink some coffee to settle my stomach. I don't think I have anything to settle stomachs unless my spice drawer does it. Or spice cabinet does it. Alright, we're on one, two, three, four, 5 pages remaining. Say 5 health pages remaining. So, let's make them good ones. As opposed to the other times when we want to make them bad ones. Alright, so we settled on a way to resolve our difficulty here. What do I mean? So we settled on a kind of compromise operation, syntax operation. Okay. So when I say if I have B is equal to the set containing as elements 2, 3, okay, I don't want to say this is interderivable with, but actually it would be interderivable with if I could somehow arrive, well, okay, so we say this is interderivable with, though this has tinges of double crosshatch. But we say B equals the set containing these elements 2, 3 is interderivable with the expression for all x. And that bracket is bad. Yeah, that was a fine drawing of a bracket. Its placement was inaccurate. Now I've wrecked the parent as well. Oh, so now for all x, x equals 2 or x equals 3 or not x is an element of B. Okay, that seems like a reasonable enough assemblage. X equals 2, x equals 3, or not x is an element of B, because there are none others. Now, one point here would be that this has to work out mechanically. Okay, it doesn't by chance work out mechanically, as it were. Though it's interesting that it does work out mechanically. I'm not quite sure what I want to say about the mechanics of this, but we'll keep going. All right, so for all x, not x is an element of B, or x equals 2 or x equals 3. Okay. If and only if x is an element of B, then x equals 2 or x equals 3. Alright. Alright, and now this. We're gonna have to make some decisions about what we mean by what we say. What I mean by what I say. Yes, Kierkegaard, what do you wanna tell us? Let's see. So, now suppose... Now this will be actually double crosshatch. If and only if... Actually, I don't know about the crosshatching. Good thing I commented it. Okay, now, so we want to be able to say... So we have this expression. X is an element of B, then x equals 2 or x equals 3. Okay. That seems innocuous enough. Does it though? And then we say... And... X equals 4. Rather, 4 is an element of B. Okay. Now this actually is what I wanted to have. Okay. Contradiction. Why? Because we have... Yeah, I feel we didn't really need to write this out. We didn't need this in blue because we now need this entire expression. X is an element of B, then x equals 2 or x equals 3. Okay. And this would be for all x. Okay. Alright, x is an element of B, then x equals 2 or x equals 3. Alright, then what? Then we say... Oh, and 4 is an element of B. Okay. Now what is the idea? So... So x, and then x, and x. Okay, and then we have, and 4 is an element of B. And then I want to say, and 4 equals 2 or 4 equals 3. Okay. Where would I type in 4 equals 2, 4 equals 3, and then It's like I would want to have arrived here with a rule for coloring and interpreting coloring that would compel me to say that this statement and 4 equals 2 or 4 equals 3 falls out of this conditional expression, and then falls out of this conditional expression in this conjunct. But does it? Well, again, that would depend on my coloring scheme, my rules for coloring. Okay. Do I have such rules? I don't know when or where I'm granting myself. Well, so this is a universal statement about all x, so any variable we can bind. If x is an element of b, then one of these two, or then this consequent expression. Okay. This consequent expression that tells us about x. Okay. Now, so we say 4 is an element of b, x is an element of b, then x equals 2 or x equals 3. Okay, well, notably, this gives us a contradiction. Okay. Maybe this should have been black, actually. Hold on. Alright. Now, what is the idea? Now, so I say, let me think here. Well, so this is and y is associative, so one contradiction spoils the bunch. So the entire thing is a contradiction. Whereas if I say x is an element of b, then x equals 2 or x equals 3, and 3 is an element of b. Alright, now we play the same game. I say, well, and that game is like saying, oh, I see a format for an expression. It says 3 is an element of b. Where can I find such an expression? Ah, there, x is an element of b. That looks like a similar expression. Why does it look similar? Because we have x over here. Well, actually it looks similar because of the b, but now what we're claiming is the same here is 3 to 3. Okay. And I guess I'll call this something different. We can go next color in line, though that would really be orange, rightfully speaking. But okay, sure, Spanish orange. Now we move on to, okay, where have I seen this x before? Ah, we see a connection here and here. Okay, and that connection is that x, and x. Okay, though maybe what I'm underlining is actually the entire expression. Okay, now what am I saying? Now we have and 3 equals 2 or 3 equals 3, and that is fine. Okay, that is a true statement, which makes all of this a true statement, which means that the truth of the entire statement rests on these others. 3 is an element of b. Though I'm not sure that resolves. So we say the truth of this entire expression now rests on the other two conjuncts. But I don't understand what it means to be true that 3 is an element of b. I mean, I mean, rather, when we're up here, it makes sense to say B is equal to the set containing its elements 2 and 3, so 3 is an element of B, but that's like a different mode of speaking. What I'm trying to get at here is that what this tries to accomplish is show that saying 4 is an element of B gives us a contradiction for other reasons. We get a contradiction out of this because of our definition of set membership, or yes, well, our yes, well, we get it out of our definition of set membership. Okay. And what is my point here? So we're saying not B equals the set containing as elements 2 and 3, and 4 is an element of B. Okay. And how do I know that? I know that because 4 is an element of B and contradiction. That's not the clearest way of saying that, but okay. Because this is a contradiction. Yeah, I'm gonna say that's not a good way of drawing that. Okay. I guess, yeah, well, the current question is about how it makes sense to talk about the truth of individual terms. Like when I say B equals the set containing as elements 2, 3, semicolon. 4 is an element of B. Alright. Now, what truth value does this have? I don't know. Now, though, if I say B is equal to the set containing as elements 2, 3, okay, and 4 is an element of B. Now, what truth value does this have? Still don't know. Okay. Now I say this is interderivable with the expression. We'll just say yeah, well, you gave it blue up there. Just keep that blue. If and only if blue and 4 is an element of B and contradiction. Okay, but that doesn't tell me sure what that tells me. B equals the set containing its elements 2, 3, and 4 is an element of B. We could suggestively put the lighter blue beneath this. Well, so if I merely had the expression B equals the set containing its elements 2, 3, and, no, rather, just that expression, and then we want to note that this isn't a contradiction. Yeah, though I'm saying, yeah, so that's my point. This isn't a contradiction. So, I mean, do we learn something by anding on the 4 as an element to B and obtaining a contradiction? But I guess not, because it doesn't mean that 4 as an element to B is false. It means that the combination of statements is false. In this case, it turns out this is a false statement in this context. But in a different problem or in a different expression, you don't have to, if you start with a true statement, you don't have to and on a false statement. No, well, you have to and on a mutually inconsistent expression. So I guess the point here is that, well, hold on, let me write this out. So we'd be saying x is an element of B, then x equals 2, or x equals 3, okay, and then that's this expression. Too many objects just lying around, ready to knock each other off the table. Alright, now, what am I saying? So it's not the case that anding on resulting in a contradiction implies that the anded on expression is false. It's that you can't have both being true at the same time. You have a contradiction, if you will. Right. So my point is that 4 is an element of B is not a contradiction. Is not itself, I guess it doesn't make sense to say of this term that it's false. So it seems to me. But rather what it makes sense to say that blue and, yeah, we should give this a color. Rather, it's the case that light blue and blue, diagram blue, is the contradiction. Okay, so my point here is that this doesn't tell us Okay, so what we could do here is say say B is equal to the set containing its elements 2, 3, and 4 is an element of B is interderivable with a contradiction. Something like that. That doesn't do the work that we want. I guess we could do... I'm trying to say does not tell us. Or does not, let me see. So observing that this expression as a whole, B is equal to the set containing its elements 2 and 3, and 4 is an element of B is interderivable with a contradiction does not tell us that 4 is an element of B is a contradiction. Slashes and they could meet at the top or something. That suggests it's like a dual operator. You'd want to use the other half of it, but I don't know how you'd use it. Now this might not make a practical distinction. I mean, certainly my symbol selection does not make a practical distinction. But what I mean rather is that this produces a contradiction. This is interderivable with a contradiction, so this expression is false. But that doesn't tell me that 4 is an element of B is false. It tells me that I can't put these statements together. It's like, suppose I have... Okay, and then I have... T or okay. Let's suppose I have an expression. I have this. Okay. Yeah, but again, this doesn't make any sense to me. I can't make any sense out of this. So now we say not. Well, okay, now if I say I can't fill in an expression in this way. Hmm. Well, and I mean, that there's a way of reading that where it makes plenty of sense. What do I mean? 4 as an element of B is not some kind of a priori contradiction. It's not a contradiction in terms. It's not by itself, it's not any kind of contradiction. It's only in this, this conjunction is a contradiction. Okay, well. Anyway, that's what we had to settle on because otherwise, this way of handling the syntax yields a contradiction when it is supposed to do so, and it doesn't yield a contradiction when it is not supposed to do so. So for all mechanical purposes, this definition works fine. Okay. So now, Theorem 99. A by E, B rather, equals B by A. Okay, actually, I don't remember how this was supposed to fit into. If and only if interderivable with A equals empty set or B equals empty set or A equals B. This interderivable distinction, this is like the kind of thing you'd want to point out to your mathematician friend. Hey, you had that mechanical construction you showed me. It turns out that the statement A equals B is interderivable with a contradiction, given how you utilize A equals B. Would you be interested in seeing that contradiction? And the mathematician says, naturally I would, because I want to fix my poorly constructed mechanical construct. Okay. A by B equals B by A. Actually, so let's see if we can go back and figure out why we wanted that expression. Is it a problem if I can't go back and figure out what I was thinking about? Probably, but also there's the question, how much time do I want to spend thinking about what I was thinking about? Okay. There's a point here. Well, the first question to ask, what am I willing to do with these quantifiers, I think. There's a curious expression. If we can group together these two for all x statements, we could extract the negation. We could say x is an element of A and x is an element of B if and only if for all x, x is an element of A if and only if x is an element of B. Now we're saying for all x, if x is an element of A and x is an element of B, then x is an element of A if and only if x is an element of B. Alright, which seems like another habitual confusion on the part of the logicians. Another habitual insertion of this confusion. What do I mean? Well, so I can, if I say x is an element of A and x is an element of B, we can engage in natural deduction and say that x is an element of A, then x is an element of B, and x is an element of B, then x is an element of A, as we did yesterday, where we say, let's see, premises. Let's see, x is an element of A, x is an element of B. Okay, now I say, I push immediately. Okay. And I say, x is an element of A. Assumption. Okay, and then I say, observe, x is an element of B. And that would be a restatement from the premises. Okay. X is an element of A. Then x is an element of B. And that is the conditional introduction. Easy game. Alright, and then I say, and then I immediately push again and I say, but have you considered that if x is an element of B, assume x is an element of B, alright, but then x is an element of A. Yes, I recall that premise. X is an element of A. Restatement, alright, and now I exit the argument and I say x is an element of B, then x is an element of A, which in common usage would have some sort of implication of causality, but in logic has no such implication of causality, so don't bother me about it. Conditional introduction again, and now I will do that should be, I guess, if anything, let's see, darker shade of green, so that I can do the lighter shade of green up here. Alright, if and only if, and this is just conjunction introduction. Alright, and then I say x is an element of A if and only if x is an element of B. Okay, that's this introduction. Okay, which would be dark green, I suppose. Something like that. Alright, now this is nonsense gibberish to me, but it makes sense to mathematicians, apparently. Logicians, anyway. So, what does that tell me? Well, this is a tautology. Okay. What use is tautology to us, though? Yeah. Interesting question here. Well, that might be the routing. Well, and most of the work ends up being done by saying that A equals B. So we say A by B equals B by A. Mm-hmm. I mean, maybe what all of this is telling me is about how I'm committing myself to interpreting these quantifiers for instance, when I say, when I say that all right, when I say that A equals B is defined as X is an element of A, then X is an element of B, and X is an element of B, then X is an element of A. Okay. And now maybe the elusive triple crosshatch. If and only if for all X is an element of A and X is an element of B, is interderivable, or I'm not sure about that one, with A equals B. Okay, now there is a way of salvaging this. I mean, I wouldn't want to say, for instance, there exists an X such that x is an element of A and x is an element of B is interderivable with A equals B. Somehow that would be absurd. I say there exists an element, at least one, such that it is an element of A and it is an element of B. Then that must be interderivable with saying that A equals B. Okay, so if I want to accept this one, well, really, if I want to accept this baffling line of reasoning that logicians tell me makes sense, the for all x quantifier has to be doing some work, because if I say instead there exists an x, then I say this is completely unacceptable. It makes no sense. Okay, but again, what do I mean when I say for all x? And there isn't a sort of consistent syntactical way of addressing that question. I mean, that I'd have to start writing out English sentences. Well, yeah, I mean, if we took these as having implicit domains, that would be less of an issue, I would think, or that would resolve. I would resolve many of my questions about these quantifiers. I think. Why? Well, so we say the universe of discourse. Yeah, let's use V. Right, V is equal to the set containing its elements 1, 2, and 3. Okay. For all x, the quantifier for all x such that x is an element of the set containing its elements 1, 2, and 3. Okay, with the idea that this would be the quantifier instead. And now in any actual application, this would not pose any kind of problem. Well, and I think the second point here would be that should have been. Right, so now what we aren't saying is that V equals the set containing as elements negative dot 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 negative 1 0 1 dot dot dot. Okay, and then saying though if I said for all x such that x is an element of V, if x is an element of A and x is an element of B. Yeah, but that's well, okay, if and only if is interderivable with A equals B. That's not what the it's not clear what this is or is not saying, though it doesn't strike me at the moment that this is saying this is true of all x. Or rather, this doesn't strike me as saying in the moment that if it is true of every x, that x is an element of A and x is an element of B. Because this would be, let's see, well, yeah, now we want to do, I guess we need to reopen. We can open up Orange. Has the garbage collector picked up Orange yet? Let's see. We could also do Spanish Orange, but oh, look how little we're getting. We have remaining. Let me see. Yeah, okay, we'll keep depth. No, we won't keep. I mean, it'll be. The idea being that we close. Yeah, we'd have to be able to. Well, that's why we close it, though. Yeah, okay. Alright, so we have orange. Alright, so I'm going to reopen a stack frame colored orange here, and I'm going to say the turquoise case is that for all x such that x is an element of V. Well, so this is a question about where the brackets are placed, I suppose. In a different way, it's a question about asking what expressions can be taken by themselves. What constitutes a sort of endpoint of an inference? What do I mean? Well, so I say x is an element of A and x is an element of B. Okay. Well, that could be one of the interpretations, if and only if A equals B and then closing bracket. And now the idea is that this quantification extends over the entire expression. Okay, though what that idea is not clear to me. Okay, but now we say X is an element of A and X is an element of B if and only if A equals B. Mm-hmm. Well, so one interpretation is to say that A is equal to the set containing as elements dot 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 negative 1 0 1 dot dot dot, and B is equal to the set containing as elements dot 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 negative 1 comma 0 comma 1 dot dot dot. Okay. And A is equal to B because they have all the same elements. Okay, that would be an interpretation. Yeah, though I don't know what the teal interpretation is supposed to be here. Hmm. That was maybe too many elements, but whatever. Right. A equals the set containing its elements 1 and 2. B is equal to the set containing its elements 1 and 2 in this case. Yeah, okay. And now, so what is the idea? Let's give this expression true green, and let's give this expression grass green. Okay. And we'll go ahead and give both of these sets 3. How about that? Okay. Actually, we could do... And C is equal to the set containing its elements 1, 2, and 4. Yeah, I don't think that's the way to do that. Now that I'm looking at it, no indeed. However, Brown should overwrite. Alright, well, we can now redo and say V is equal to the set containing as elements -1, 0, -1, 0, 1, 2, 3, and 4. Alright. And now the idea. Okay, and now we get 1, 2, 3, and then we get 1, 2, 3, and then we get 1, 2, and 4. Okay. Right, and then we get contradiction, and then we get contradiction and contradiction. Okay, having as a default case that contradiction covers all 3 lines seems reasonable, but let me write that out more largely. Yeah, that's a good phrase. I will write this out more largely. V is equal to the set containing its elements -1, 0, 1, 2, 3, and 4. Okay, and we're saying, and I'll do contradiction, 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 and then contradiction, contradiction. Okay, and what does that do for us? Well, this gives us maybe a more well, so we're trying to come up with a way of interpreting this. X is an element of A and X is an element of B if and only if A equals B. For all X where X is an element of V, or for all X, whatever that means, but in this case, yeah. X is an element of A and X is an element of B. Well, I mean, the idea would be that this never has. If this has no mixed truth value expressions, so to say we have -1 is an element of A, and -1 is an element of B. Okay, and we have 0 is an element of A, and 0 is an element of B. Okay, and then we have 1 is an element of A, and 1 is an element of B. And we have 2 is an element of A, and 2 is an element of B, and we have 3 is an element of A. Yeah, I shouldn't have used so many examples, but whatever, 3 is an element of B. Don't really gain much by having it. No, not too much. 4 is an element of A, and 4 is an element of B. Okay. Now, the idea is that actually, that could be poppy red, but yeah, too late. Alright, whatever. Now, so contradiction and contradiction, both of these are false. Both of these will lead to a contradiction given our syntax for what we do with the statement that A equals the set containing these elements 1, 2, 3, which is as close as we get to a false statement in this context, I guess, or a contradiction rather. Alright, so this also is false and false. Okay, and then this is true and true. True and true. True and true. And then contradiction and contradiction. Okay. Now what? Well, relatedly, though, yeah. If we say, we can just start at 0. 0 is an element of A. Okay, is an element of A, and 0 is an element of C. 1 is an element of A, and 1 is an element of C. Okay. Let's see. 2 is an element of A, and 2 is an element of C. 3 is an element of A, and 3 is an element of C. And 4 is an element of A, and 4 is an element of C. Alright, and now this is contradiction and contradiction. Now this is true and true. Okay, and now this is true and contradiction. And then this is true and contradiction. Okay. Alright, now what is the idea? Curious. This is like saying, well, it's like describing an operation, a procedure that we could undertake. Like if we said, I have a list. I don't like that symbolism. It's just sort of, I don't know, off. Oh, whatever. So we have, we say 1 is an element of A, and 2 is an element of A, and 3 is an element of A. Okay. And then we have a corresponding list. One is an element of B, and 2 is an element of B, and 3 is an element of B. Okay. And now we have a zipping operation. Okay. The zipping operation is that I take, sure. Okay, but to wit, I am looking at, okay, I look at the color. Rather, I look for like I scan each of these. Okay, though I would get this one first because it's in the list. But okay, so I'm kind of losing it with this. So the idea though is in this interpretation, the point about saying So we could imagine this as describing a procedure. Okay, if one of these statements is true, x is an element of A or x is an element of B, then both are true. Okay. So yeah, that was a little bit of a management issue. Right, we have these groupings that we can make. Okay, and then some appropriate suitable expression that there are no other elements. Okay, and now we're saying, this is like saying, let's see. X is an element of A and X is an element of B is interderivable with A equals B. Double crosshatch. X is an element of A or X is an element of B if and only if, with no crosshatch, which I will note. X is an element of A and X is an element of B. Okay, but that is like an empirical claim, or rather, so to say, if we say X is an element of A or X is an element of B, and then the non-crosshatched biconditional, this is not about derivability. This is about let me think. Well, so we could work through these expressions. The point is that we would need to grant the truth of this biconditional in order to accept this. So I am thinking. And how we arrive at that conclusion is is through this example. Okay. Where in this example we're saying what makes this truth claim, rather what makes this conjunct interderivable with A equals B is that we get the same truth value for every x. So if one is false, both are false. If one is true, both are true. Though it would be interesting to ask, what do we get? It would also be interesting to ask, how does the calculus lesson continue? Let's see. One last calculation for old time's sake. X is an element of A or X is an element of B. Then X is an element of A and X is an element of B. Okay. And X is an element of A, and X is an element of B, then X is an element of A, or X is an element of B. Okay. I'm afraid this is going to end up being nonsense gibberish, but actually we could reduce this to P or Q, then P and Q. And P and Q, then P or Q. Okay. So this is going to give us not P and not Q. Or P and Q. And not P and not Q, or P or Q. Okay. Not P or P and Q. Okay. And not Q or P and Q. Okay. Not P or P. And not P or Q. And P or not Q and Q or not Q. Alright. Tautology. Tautology. Okay. Interderivable with. Let me see. P then Q and Q then P. Okay. If and only if, or this would be colon, or better to say colon. Now we're going to have, let me see, X is an element of A, then Q, X is an element of B, and X is an element of B, then X is an element of A, incidentally, is our statement of equality. P or Q or not P. And P or Q or not Q. Which is a tautology. Okay. Which makes the entire expression a tautology. What did that prove, if anything? No idea. Well, it boils down completely to saying, oh, yes, indeed. Well, I mean, it gives us, that this is all interderivable with A equals B, interestingly. It's biconditional because we can introduce a tautology whenever it pleases us to do so. Okay. Meaningless gibberish. Yeah. And the point of this, again, is that I feel like this tells me something, but I don't have anything. I don't have any context within which to interpret it. We wanted to express this sentiment that we had the same truth values for each of these expressions, that this statement for all x is an element of A and x is an element of B is interderivable with A equals B. That only makes sense if we're saying that, well, it makes sense in this way. We can interpret it here where we say A is equal to the universal set, and that's how we interpret for all x is an element of A. And then B is the universal set as well. That's how we interpret for all x is an element of B. And now A is equal to B because they're both the universal set, and universal set. Every set is equal to itself, I suppose. All right, and then here we say, here we go with a different routing, which is that saying for all x is an element of A and x is an element of B is a statement about the truth value of the conjunct, but it's a statement about the truth value of the conjunct only under the condition that you care about it, as it were, which was the point of this list operation example. What do I mean? The only elements I care about, the only elements I investigate for the truth of this claim are those that I find in A. So to say, when I'm saying x is an element of A and x is an element of B, okay, which x's do I care about? Well, ostensibly all x's, whatever that means. But then I'm saying in an actual process where I'm comparing two sets for equality, I would check one element at a time. Okay, now this would amount to a procedure. This assertion has this kind of correlate in a procedure where I say, where I say the x that I care about, or that this is a statement specifically about the x I encounter in the course of some procedure, and that's what makes sense of this expression. So for all x, if it's true of one, it is true of both. If it's not true of either, then I don't check. There's never an impetus to check any of the elements that aren't elements of either. I am motivated to check an element by that element being in one of these. Okay. So we have like a process. Oh yeah, well we could have, I guess we didn't want to close that. So looking back, this was a notebook management error. And we didn't end up closing red. Yes, well I guess the alternative case might have something to do with the bracketing. I guess we want this quantifier to bracket the entire expression. I guess let me doodle out this point. So list 1 is an element of A, 2 is an element of A, 3 is an element of A. All right. And now I say, let's see. Meaningless gibberish, yeah. Okay. Alright. Yeah, we can do yellow, I guess. Okay. Sure. Alright, now we say yellow, for all x not x equals, I just want to say it's empty. As if I have extracted all of the elements. Okay. Whereas with 1 is an element of A and 2 is rather C. 1 is an element of C, 2 is an element of C, 3 is an element of C. Now B dot 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 rather 4. Now, in this case, we would search through B for an element where that says 4 is an element of B, and we would not find it, and then we would have mixed parity. But the point of this is that I'm going to put here for all x if I have an occasion to check x, x is an element of A and x is an element of B. Okay. Now I will take a break. We don't have so much time left. I don't think I'm going to exercise when I come back. Okay. Perfect. Alright, I can't mute using my hotkey anymore. I have to do a trick shot on the mute button. Looks like this is number 4. Can always cross it out if I'm wrong. Structure and interpretation. Okay. However, we don't need that now. Oh, 5. Proof 5. We have a head start. Let's maintain it. Okay. Now what? Calculus. We need a book. The calculus book, if you will. Alright, I think we can probably launch in on the exercises. For the following exercises, I'm going to blast myself with a space heater a little bit here. For the following exercises, evaluate the given exponential functions as indicated. Accurate to 2 significant digits after the decimal. Okay. 229. F of x equals 5 to the x. F of 3 is equal to 5 to the 3. Should we do the author one better and give infinite digits after? F of 1/2 is equal to 5 to the 1/2, and f of root 2 is equal to 5 to the root 2. Yeah, that's the way it's done. 230. I think we can skip these first ones. I think we've not so much of a puzzle. Let's find and replace. Okay. For the following exercises, match the exponential equation to the correct graph. Alright, that doesn't need my notebook either. Okay. So, do we want some process of elimination here? So, let me do here. So we have 1 minus 5 to the x Okay. So that's going to have an asymptote of y equals 1 because as x tends towards negative infinity, 5 to the x tends towards 0. Okay, so... suspicious. Suspicious. Well, actually, if we do, let me think here. The suspicious aspect here is that we have 1.5 as the numbering. Curious selection. So if we have... we would have a value of y equals negative 1 if we did not have the offset. So the offset is telling us that we have... well, actually, we might be able to produce an inference here. What do I mean? Actually, no. I was going to make this point that we have, at x equals 0, we have y equals 0. Okay. Now, if we get rid of the 1 and we simply add negative 5 to the x, at x equals 0, this would be positive 1. Wait a minute. No, it'd be negative 1, right, because we would have negative... the negation happens after 5 to the x. So we would have negative 5 to the 0, which is negative 1. Okay, but adding the 1 translates the graph, translates the plotting. Okay, however, we also have, let me think here. Well, we have plus 2, but here x equals 0, and we would have 3, which we don't have. Okay. Now, if I have x equals 0, well, x equals 0, we have 2. X equals 0, we have 1/3. X equals 0, we have 1. So f would match up with 234 is f. All right. Now what do we want? So this similarly plus 2. So at x equals 0, we have... no, x equals 0, we have 3. Right, that's what we expect, because 1/2 to the 0 is 1 plus 2 is 3. So 0, 3, and asymptotic to 2. Okay, as we increment x, we are multiplying 1/2 by 1/2 repeatedly, which is making the contribution from 1/2 to the x tend towards 0, so we have asymptote at 2. Fine, so... well, okay, 233 is D. 234 was F. All right. Now, what do we want? So one of these is going to be exponential as x is going to increase exponentially as x increases, and its value at x equals 0 will be 2. Okay. There we go. So 238 is C. Okay. So we're out of this, this, and this. Now here we're going to have a value of 1 at x equals 1. So we're going to have a 0.11, and then past that point it will be exponential. That, okay, does that description apply of any other? So we could try to make this a logic game, though I'm trying to solve the problem before I play the logic game. Okay, let's try to play this as a logic game. Okay. So we say A, y equals 4 to the negative x. B, y equals 3 to the x minus 1. C, y equals 2 to the x plus 1. D, y equals 1/2 x plus 2. Okay, E, y equals -3 to the negative x. F, y equals 1 minus 5 to the x. Okay. Okay, now what? Okay, so I'm going to say green. Well, let's so we do x equals 0. Yeah, we could have shifted that down. Where did I put my eraser? Alright, we're gonna sacrifice this. And then... sure, okay. So if I say 0, the ordered pair is 0, 1. Okay, the ordered pair 0, 1/3. Right? The ordered pair, whatever. The ordered pair 0, 2. The ordered pair 0, 2. Alright, the ordered pair 0, negative. No, wait. 0, 1. And the ordered pair 0, 0. Alright, now we have a repeat. Close that ordered pair. We have a repeat. We have 0, 1, 0, 1. And then we have a repeat here. 0, 2, and 0, 2. And then the odd ones out are these heterogeneous cases. Okay. Sure. Now what? Well, so that means, let's see, we can name those, we can figure out those, okay? Well, actually, so it's a critical point, or an interesting point here to follow up on, that we have the range of this set. Well, okay, if we say the domain for round 1. it's kind of overkill on coloring. It makes the coloring less meaningful. If you have to color everything of a sequence, you shouldn't color any of it. You should set it up so that you don't feel the need to color any of it. So I am thinking, but okay. So the domain is equal to 0. Okay, though then this could be indicative of how this domain statement down here is working. Range is equal to 1/3 and 1 and 2. Okay. And now what is my point? Let's see. Oh, I missed 0. Yep. Okay. Yeah, and now we want to make this complicated point that 1 is greater than 1/3. Okay. 2 is greater than 1/3. That's not quite how I want to phrase this observation. Maybe it is. 1 is greater than 1/3 and 2 is greater than 1/3. 0 is an element of the integers. And not 1/3 is an element of the integers. Alright, and we have thereby distinguished our relevant cases. Okay. So now, after round 1, we have 0, 0, which is 234. Okay. And we have 135. So if we look through all the graphs, there's only one there's only one value where at 0 we have a non-integer value. Okay, I believe it. And that's 235. Okay, so now what do we want to do? We want to take round 2. What do we do in round 2? So we could take the two cases. Okay. We take the two cases where we have 2 as the output at 0. That's an option. Okay, what do we want to do with those two cases? We want to choose the input -1. Interesting. -1 here will give us 4. -1 here will give us 1. Okay. Let's see. -1. 1. And then -1 and 4. And we might as well apply that test to the remainder. So -1 will be 4. Ah, interesting. Yes. Now up here, -1, 4. Okay. And then down here, -1 is -3. Okay. Now what is the idea? Well, funnily enough, we can't distinguish these two cases, but with the additional property that 0, 2, so -1 orange, and then let's see, 4, 1, 4, 3, so sure, -3, 1, 4. Okay, so that's going to give me that. So these 4s don't differentiate each other. This is the only negative value at -1. So if we go back, -1, positive, 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 though we didn't actually check that one. -1, -4. That shouldn't be -4. Hold on. -1, -1. -1, +4, -1, +4. -1, 1. -1, -3. Well, so on the cases that we've already cleared, this would be 3 to the -1 minus 1 is 3 to the -2, which is still positive. Oh, I'm confused. Yeah, I got confused here. Graphs, what are they? This is -1, -3. None of the others are negative in y value. They're negative. I looked at the negative x value and then I said, look, the x value is negative. 237. All right. And now there's only, so back here the point was we might wonder, how much do I have to be able to distinguish? How much do I have to be able to differentiate? Here we granted ourselves the ability to distinguish between, well, yeah, it's like a chain of reasoning we could apply in a program, in a procedure, where let me think here. Like we have 1/3 and then 0. So there's this dividing line where we have the 1/3. Everything above that is an integer. Which we didn't really write that out, but okay, the idea would be that we have this non-integer value. Everything below it is 0. Well, the only thing below it is 0. And then we can distinguish between these two on the basis of the fact that this isn't an integer and this is. Okay. Fine, and now what? Well, how do I distinguish between 1 and 4? Do I simply want to grant myself that ability? Well, I could look at the graphs and I could say that 2 of the remainders that I haven't cleared by other means, like differentiating between negative and positive, 2 of the remainders have the same y value and 1 of them doesn't. I'll take the shortcut of looking for the one that isn't. Let's see, so this is -1, 1. $238. Okay. Then what? Now we have to distinguish between the two cases of -1, 4. There's a copy of -1, 4. Okay. And another copy of negative 1, 4 is here. Okay. Yeah, and here we just say asymptotic to 0. I guess. Okay, so this is 236. C equals 0. Okay, and this is 233. C equals 2. Okay. Very well, I'll call that a problem completed. For the following exercises, sketch the graph of the exponential function. Determine the domain, range, and horizontal asymptote. Let's see. Guess we can get one of them in here. Or we can preserve this for illumination. I'll preserve it for illumination. Alright. Okay. 239 f of x. Hold on, let me get colors back into position. Okay. F of x equals e to the x plus 2. Don't want to leak any math. Okay. That left bracket needs a little bit of help. All right, so e to the x plus 2. Okay, there are no negative values actually. Would be a point to make here. Alright, so I have 1 and then I have 2. Okay. And so now I would have 3. Right, this is off to a bad start with regards to sketches. So, e to the 0 plus 2 is equal to 3, colon, the ordered pair, 0, 3. Alright. Now, what is e? You can't say it's infinity. No. If I were counting up by hundredths or thousandths, it would be infinity, but no. 2.7, yeah, but that's meaningless gibberish. Students would leave my class saying, "There's no such number as E. Do you take me for a fool?" And then I would get reprimanded and fired. E. There's no such number as E. Yeah, well, what are you supposed to plot here is the question. I mean, I could just say all exponential functions look the same, and then, or I could say 1, and then we have 4 and 5, and then it would be like up here. Okay. E to the 1 plus 2 is equal to 5.7. Okay. Alright, I think that graph was a little lacking. Spindly line here. Oh well. Now f of x equals negative 2 to the x. Okay. Yeah, should have given myself more space up than down. Which actually, isn't that the more mathematical skill, looking just a little bit ahead and knowing how much space to give myself and in what direction? Right, let's see. Negative 2 to the 0 is equal to 1, which gives me the ordered pair 0, 1. Negative 2 to the 1 is equal to negative 2, which gives me the ordered pair 1, negative 2. Negative 2 to the negative 1 is equal to negative 1, 2, rather negative 1 half, which is equal to the ordered pair negative 1 comma negative 1 half. Okay. Okay, so now we're going to have 0, 1. Okay. And then we're going to have 1, negative 2. Okay. And then we're going to have negative 1, 1 half. Negative 1 half. Hold on. Negative 2 to the 0 is equal to 1. That makes sense to me. Negative 2 to the 1 is equal to negative 2. Negative 2 to the negative 1 is equal to negative 1 half. I confuse myself? Hold on, let me get my graphing calculator here. Okay, let's not be confused here. Order of operations. Whoops, this is -1. And I will hide my shame here and remove that. Alright, so 0 at -1. Okay, and then we have -1/1 and this is supposed to curve, which it does ever so slightly. And then this, well, I mean, there are other critical characteristics here. Yeah, actually, the same point here that this should be asymptotic to 2, which would be a feature of the graph that we'd want to include. Okay. As it stands, this just looks like a line. Yeah. Now that I'm thinking about it, why is this asymptotic to 0? Let me think. So I have -2. Wait a minute. Oh, right, because... Wait a minute. Okay, let's do a little bit more extensive. Alright, so A is equal to the set containing its elements -2, -1, 0, 1, 2. Alright. B is equal to the set containing its elements. So -2. Okay, so that would give me well, that's not the problem. -2 would give me -1. Wait. Right, we keep forgetting about the order of operations here. This is -2 to the x. Okay, that's why this is a legal function. Otherwise, there would be problems here where, for instance, with 1/2, if this was instead, yeah, let's see, -2 to the x. Okay, we can do this with case A, case B. Alright. So B will be equal to, so I choose -2. That'll be -1/4. Okay, I choose -1, that'll be -1/2. I choose 0, that will be -1. Okay, I choose 1, that will be -2. I choose 2, that will be -4. Okay, now a teal, rather a turquoise. Yeah, I'm having a lot of fun with the set theory and the keeping up with colors. I should be trying to do the same, which is hence this. Yeah, so now if we do the same thing, A is equal to the set containing its elements -2, -1, 0, 1, and 2. B is equal to... So now we're going to have Well, that would be, let's see, -2, so positive 1/4. Okay. And now -1 will be -1/2. And now 0 will be +1. And 1 will be -2. And 2 will be +4. Yeah. Now, it isn't only a problem that these disagree, it's also a problem that, let's go back to turquoise here. A is equal to -1/3, -1/2. Yeah, okay, -1/2, -1/3. And 1/3 and 1/2. B is equal to negative, the set containing its elements, -1 divided by √2. Then -1 divided by √3. Rather, -1 divided by 2 to the 1/3. A little bit involved here. Let's see. And then this would be -2 to the 1/3 and -2 to the 1/2. Right, okay. Now we have, let's see. Alright, B is equal to, okay. Oh, did I structure this right? I might not have structured this right. Well, it's still fine. So we take -2 to the x, -2 to the -1/2 is equal to, let's see. -2 to the, rather 1 divided by, well, okay. Yeah, okay. 1 divided by 2 to the 1/2, -2. Okay, this did not turn out. Hold on. 1 divided by negative 2 to the 1 half, which is a system error. Oh no, I hear a knock at the door. It's the mathematics division of the NSA. System error. Sure. Now what we wanted to do, actually, it struck me a little bit too late, is that we could have had negative 1/3 first and then had a legal value and then only afterward cut short. Anyway, I think that's enough for today. I'm going to continuing looking into real life stuff. Okay. See you soon. In all likelihood, I will be back tomorrow for more exciting mathematic adventures. Okay.